Let's begin today by discussing function composition. So we have sets A, B, and C. F is a function from A to B. G is a function from B to C. And then we define the composition of F and with G. This is written this way. This is read Decompose F. This is a map that goes from A to C, and this is defined by Decompose F of some value A. This is G of F of A. So F of A, this is an element in B, and then B is the domain of G. So we evaluate G at F of A, and this lands us in C. In the picture, which we will do an example in just a moment, but the picture is like this. We have sets A, B, and C, and then we have F maps A to B, and G maps B to C, and then the composition maps A to C. Now, absolutely, this is a very important observation that we must have. In order for the composition to be defined, we must have that the image of F is contained in the domain of G, right? Because you're evaluating G at an element in the image of F. So you must have this in order for the composition to be defined. Now, what's another comment that I will make? I will make note number 2, and then we will get into some examples. The domain of this composition is always the domain of F, right? We see it here, or we see what you're putting inside F here. It's the set A. Well, maybe I'll write this. The image of Decompose F, well, this is a subset of the image of G. It is not necessarily equal to the entire image of G. Here's our first example. We're given F and G. Let's find Decompose F, or explain why it is undefined. And then we will find F compose G, or explain why it is undefined. So let's do part A first. Well, maybe I will start by drawing this picture, and then we can write Decompose F in terms of ordered pairs. So we have A, we have B, we have C. Now the domain of F, we see this. It is 1, 2, 3, and 4. And then I will start here. The domain of G, this is the set B. This is 2, 3, 4, and 5. And then we can 2, 7, just 2 and 7. That's all I need for C. Certainly I could add more things if I wanted to, but I will just put 2 and 7. And then I will think about G as being on 2, for example. Okay, now let's draw some arrows. F maps 1 to 2. F maps 2 to 3. F maps 3 to 4. And F maps 4 to 3. Okay, this is an example already. What I said, we absolutely must have the image of F contained in the domain of G. And we see that here, just as an important comment. The image of F is the set 2, 3, 4, and the domain of G is the set 2, 3, 4, 5. And certainly the image of F is contained in the domain of G. Now let's draw G. And green was F. G maps 2 to 7, 3 to 2, 4 to 7, and 5 maps to 2. Here. Now, let's write out the ordered pairs of Decompose F. Decompose F is defined because, well, as I commented, the image of F is contained in the domain of G. And how we write out ordered pairs, we just follow the arrows. So we will write out ordered pairs here. One maps to 7, 2 maps to 2, 3 maps to 7, and finally 4 maps to 2. This is Decompose F. Now, this diagram, which we like to look at for functions, and especially functions with between finite sets, we don't need to write that in order to calculate Decompose F. For instance, you just start here. Start with F. 1 maps to 2, 2 maps to 7, and so Decompose F has 1, 7. 2 maps to 3, 3 maps to 2, and so Decompose F has 2, 2. 3 maps to 4, 4 maps to 7, and we see 3, 7, and finally 4 maps to 3, 3 maps to 2, and we see the ordered pair 4, 2. So that is how you can write out the ordered pairs, just looking at the ordered pairs for F, the ordered pairs for G. Now, a comment to my other note I had when I defined the composition. In this case, you see the image of Decompose F is the set 2 and 7, and this is the same as the image of G, but it doesn't need to be. Now, let's think about B, F compose G. What I would do to think about this function is here I will put the domain of G. Here I will put the domain of F, because in order for this to be defined, F compose G, I would need the domain of, the image of G to be contained in here, the domain of F. And here I will put the image of F. So the domain of G is 2, 3, 4, and 5. The domain of F is 1, 2, 3, and 4. And the image of F is 2, 3, and 4. Okay, so let's do F first. F maps, this one we already had, 1 to 2, 2 to 3, 3 to 4, and 4 to 3. In order for F compose G to be defined, I should be able to put an arrow coming out of each one of these over here. Okay, well, you see, hopefully you see, this I cannot do because some of it's okay. 3 goes to 2 and 5 goes to 2. But now, what am I going to do here? There's no 7 here. So I could add this little, maybe out here, add a 7, and this is really where this maps, and this is where this maps, right? 2 maps to 7, 4 maps to 7. But the problem is, there is no, you can't go further. This element 7 is not in the domain of F. So in this example, F compose G is undefined. And the reason is that the image of G, which is the set 2, 7, this is not a subset of 1, 2, 3, 4, which is the domain of F. And so for this reason, we cannot make the function composition going in this direction. First you do G, then you do F. My next comment is as follows. When you have both F compose G and G compose F defined, they may not be equal. In fact, generally, they are not equal. Sometimes, as we will see, they are, but generally they are not. So let's look at this. I kept the exact same F, and then I changed G. This is a new G. But in this case, well, let's justify this. we will see both F compose G and G compose F are defined. But how would we justify, or how would we know it's defined? What's the image of F? The image of F is 2, 3, 4. And the domain of G is 2, 3, 4, 5. Okay, image of F is contained in the domain of G. And so this means that if you take G compose F, this is defined. And we will list. Oh, let's do this now. Then we'll talk about the other direction. Let's list ordered pairs. You could certainly draw a picture, but I will just list the ordered pairs looking at these two. So 1 maps to 2, and 2 maps to 2. 2 maps to 3, 3 maps to 1. 3 maps to 4, 4 maps to 2, and 4 maps to 3, 3 maps to 1. So this here is G compose F, okay? Now, let's talk about the other way. Well, the image of G is what? The image of G is just the set 1 and 2. And the domain of F is the set 1, 2, 3, 4. What do we need? We need the image of G to be contained in the domain of F. And this is definitely the case because 1, 2 is a subset of 1, 2, 3, 4. And this means that first we do G and then we do F. This is defined. So this is an example, unlike the last one, where both F compose G and G compose F are defined. Okay, well, let's write out ordered pairs here. We will see we get a different function. So for F compose G, we start with G. 5 goes to 1, 1 goes to 2. 4 goes to 2, 2 goes to 3. 3 maps to 1, 1 maps to 2, and 2 maps to 2, 2 maps to 3. Okay, this is F compose G. Now, if you stare at these, you notice these are not equal as sets. They are not equal as relations. They are not equal as functions. So without a doubt, we notice this here, right? That note, G compose F is not equal to F compose G. In fact, they don't even have the same domain, right? The domain here is 1, 2, 3, 4. This is an important observation. 1, 2, 3, 4. And the domain over here for F compose G is a different set. It's 5, 4, 3, and 2. So if you have two functions that have different domains, there is no chance those functions are equal. But we see it explicitly here by listing ordered pairs. And this is an important observation. Let's do an example where F and G both map between infinite sets. F maps R to R squared, and G maps R squared to R. And here are the maps. F of X is X squared, comma, X plus 1. This is an ordered pair. This sits inside R squared. And G of YZ, so Y and Z are both real numbers, you just multiply. We get Y times Z, which is a real number. Well, first let's think about G compose F. You see, we start with F. This was what happens first, and this is a real number. Then we map into R squared, which is the domain of G. And then G maps this to R. G compose F maps R to R. And F compose G, here, this one, G happens first. So this starts in R squared. G will map an element into R, and then F takes that element in R and maps to R squared. So F compose G maps R to R squared. Well, now let's think about a formula. G compose F of some X. this would be g of f of x. F of x is the ordered pair x squared x plus 1. Now we apply g, and g takes an ordered pair and multiplies. So we get x squared x plus 1. This is a formula for Decompose F, mapping a real number to another real number. Now for F compose G. F compose G, this takes in, say, a yz, where y and z are both real numbers. Now the first thing that we do is we apply g, and this multiplies. So this would be f of y times z. And now we have a real number, and we apply function f. This would be yz, well, that's yz quantity squared. I'll write it as y squared z squared, and then we have yz plus 1. And this gives a formula for the composition in this direction, F compose G. Now let's define the identity function. Here A is a set, and the identity is denoted this ID sub A. Identity function maps A to A, and this is defined as follows. Well, the identity of some little a is just little a. So this maps each element to itself. Now, we can make some observations. If you have a function from A to B, for example, well, first you can do f. This would land you in B, and then you can do the identity on B. This is, in fact, the function f. We could also, for instance, first we can do the identity on A. This maps A to A, and then we can do f, and this is also f. This might not be that exciting because the identity just maps each element to itself. What I have drawn here, over here, is just an example showing this, where I have a function f which goes from the set 1, 2 to the set 3, 4, 5. So A is the set 1, 2, B is the set 3, 4, 5. And then first I do f, then I do the identity on B, and that's this one. And then down here, first I do the identity on A, and then I do f. And you see both of them are equal to f, which is what I wrote here in blue. You can check this because f is here in green. 1 maps to 4, and 2 maps to 5. So if you look at either of these compositions, we get 1 maps to 4, and we get 2 maps to 5. So this is just an example of this statement. Now, let's talk now, we'll go back to this concept of 1 to 1 and onto and talk about bijections. This is something that I mentioned in the last lesson, that when you have a function from A to B, if the function is both 1 to 1 and onto, this is called a bijection. We need both. Now, why are bijections so fabulous? Well, it is a theorem, I'll say proposition, if f from A to B is a bijection, then f inverse, and this, we discussed what this was. This is the inverse relation. This is a function from B to A. And it's called the inverse function. Maybe I should write this. Okay, well, proof. Let's let f from A to B be a bijection. Now, when I work with the inverse relation, or in this proof, I'm going to be using the relation type notation because it's easier to work with, because right now all we know is F inverse is a relation, right? It's where you interchange all of the ordered pairs in F. We will use that F is onto and that F is 1, 2, 1. Onto, if we write this in relation notation, it says that B is equal to the set of B and B such that AB is in F for some A and A, just that the second coordinates, right? That this is all of B. Now, if we write this in terms of F inverse, we would interchange pairs. So this is also the set. I'm just writing it differently of B and B such that BA is in F inverse for some A and A. And this says that every element in B appears in at least one ordered pair say BA in F inverse. Now, F is 1, 2, 1. Therefore, this is an implication. If, say, A, B, and CB are in F, then A equals C. This is exactly what 1 to 1 means, but written in this relation notation. This would say F of A equals F of C, then A equals C. This is 1 to 1, this implication. Okay, equivalently, rewriting this exact same statement, we have if BA and BC are in F inverse, then A equals C. So 1 to 1, which F is, it's a bijection, says this about the inverse relation. Now, what does this say? Well, this says that every element in B appears in no more than one ordered pair. Say B comma A in F inverse. And well, this was similar to what we talked about in the last lesson. If we have every element appears in at least one, and every element appears in no more than one, together every element B and B appears in exactly one ordered pair, B comma A in F inverse. And this says that F inverse is a function. This is our conclusion. This is what we have proved here. But it used that F was both 1 to 1 and onto, and we get that F inverse is a function from B to A. Now, what I would like to discuss is, this is really the reason why I introduced the identity function, because when you have a bijection, we just proved F inverse from B to A is a function. But it also satisfies this here, F compose F inverse. Well, this goes from B to B, and this equals the identity on B, and then F inverse compose F. This maps from A to A, and this is the identity on A. And this is not too terribly hard to prove using relation notation, kind of like I just did in this proof that F inverse was a function. But what I'd like to do is do an example. Here is an example of a bijection. Well, just as a comment, before we get too far into this, notice that the set A, which is the domain of F, is 1, 2, 8, and 9. And the set B, which is the image of F, is 4, 7, 5, and 10. And as I mentioned, F from A to B is a bijection. So let's compute the inverse. Well, we know the inverse relation. You just interchange the ordered pairs. But then let's compute F compose F inverse. We should see the identity on B. And F inverse compose F, we should see the identity on A. First thing is F inverse. This is the inverse relation. This is 4, 1, 7, 2, 5, 8, and 10, 9. Now we start composing. If we take F compose F inverse as a set, first we do F inverse, right? So 4 goes to 1, and 1 goes to 4. 7 goes to 2, and 2 goes to 7. 5 goes to 8, 8 goes to 5, and finally 10 goes to 9, and 9 goes to 10. So 10, 10. In fact, you see this is the identity on B. 4 goes to 4, 7 goes to 7, 5 goes to 5, 10 goes to 10. Okay, let's do the other way. F inverse compose F. So first we do F. We should see the identity on A. First we do F. 1 goes to 4, 4 goes to 1, 2 goes to 7, 7 goes to 2, 8 maps to 5, 5 maps to 8, and 9 maps to 10, 10 maps to 9. You see, this is the identity on A. In fact, let me write that. This is the identity on B. This is the identity on A. And so this is an example that makes us think about this statement. It illustrates this statement. Let's end with this example. We have a function from R to R defined by, well, it's just 2x plus 4. And I'm telling you, it's a bijection. You could check this if you want, 1, 2, 1, and on 2. But we want to find F inverse. And we will compose in each direction and see that we get the identity. How could we do this? You might have done this type of calculation before in another math class. We have y here as a function of x. What we want to do is solve x in terms of y. So we would have y minus 4 is 2x, and now just divide by 2. We get x is y over 2 minus 2. So this suggests I define as follows, y over 2 minus 2. Now, let's do this. This would be of y. And let's do this. We should get y here when we compose. And here we should get x. That would say we have the identity when we compose in each direction. This would be f of, well, f inverse of y is y over 2 minus 2. And this is 2 times y over 2 minus 2, and then plus 4. What do we get? We get, here, this is y minus 4 plus 4, which is y. And so in fact here, we do see composing in this direction, at least we get the identity on real numbers. Now about here, in this direction, we would want f inverse of 2x plus 4. Now, I put 2x plus 4 into this. This would be 2x plus 4 over 2 minus 2. And this is x plus 2 minus 2, which is x. And again, we have f inverse compose f of x is x. So this is the identity, and this is what we were just discussing. That when you compose in each direction, f compose f inverse compose f, you get the identity.